Welcome to lecture 23 of Introduction to Quantum Field Theory. In this lecture, I will talk about symmetries and conserved quantities. Recall that in lecture 22, we discussed the action for a complex scalar field. In Minkowski space, we found that an action for the complex scalar field is given by this expression here, where we have the kinetic term and the potential terms. And since the action has to be real, it typically consists of quadratic forms such as phi star, where phi star denotes the complex conjugate of the scalar field phi. We note that the action, as written in this equation here, in addition to Lorentz invariance, has an additional symmetry, namely a symmetry under the transformation where phi goes to e to the I alpha times phi, where alpha is an arbitrary real constant. In this lecture, I want to discuss some of the consequences that this symmetry has for the field theory. I'll start by writing down the action as an integral over the Lagrangian density L. From the invariance of the action, we can get the classical equations of motions, such as requiring that S is invariant under the changes of phi. So S goes to S prime. If it's invariant, that's the same as S. And that's the same as saying that delta S, which is defined as S prime minus S, is just 0. Specifically, what we do is we'll calculate the variation of the action with respect to varying the fields. So using the Lagrange density L here, we have that delta S is given as the integral over x, dl by d phi, delta phi, and the variation of the Lagrangian density with respect to the d mu phi, which we sort of can consider as an independent quantity. And we have the variation of this term here. Since we have a complex scalar field, there are also the corresponding terms, the corresponding variations with respect to phi star and d mu phi star, because we treat phi star and phi as independent fields. Using the chain rule, we are able to rewrite these expressions here as the total derivative of some expression minus a term where the derivative is acting on the other part of the expression here, such that we freed out delta phi in the terms that have the variation with respect to the d mu of the fields. If we do so, then we get an expression where we have delta phi just sitting in front of the integrand, and by varying delta phi arbitrarily, we get the classical equations of motion. So these are just the requirement that the integrand multiplying delta phi has to vanish, and these just give us these constraints here, such as dl by d phi minus d mu, dl by d mu phi is 0, and the same for the variation with respect to phi star. Plugging in the explicit form of the action that I gave at the beginning of the lecture, these equations of motions can be written in explicit form, for instance here for the field phi star and here for the field phi. Of course, we can take these equations of motions and fill them back into the expression that we had for the variation of the action given in equation 23.3. And if we do so, then we find that delta S is just given as the total derivative of this expression here. Clearly, since this is an integral over a total derivative, and the integral here is over all of space-time, we'll have that this integral here is vanishing as long as the integrand here is well behaved as infinity because of Gauss's law. As a consequence, we find that the variation of the action delta S is actually exactly equal to 0 as long as this variation here is well behaved and we don't have any restriction on the specific form of delta phi. So to linear order in delta phi, because this integral is an integral over total derivative at infinity, vanishes regardless of what delta phi is. Any small delta phi will give us vanishing variation of the action. Another thing we can do is we can consider putting the system into a box. Putting the system into a box does not change the equations of motions for the fields. So we can consider the variation of the action in a box where we have restricted the integration over some box of a specific shape and size. And the only term that can contribute is this total derivative term here that we found before. If the symmetry, if the variation of delta phi that we are considering is an actual symmetry of the system, the action is invariant, so delta S box has to be 0 if delta phi is a symmetry. If it's not a symmetry, then basically in a box, this variation would not be 0. We note that the action that we have explicitly stated down for the complex scalar field, given in equation 23.2, does have a specific symmetry. Namely, it has a symmetry if delta phi is just equal to I alpha phi of x. We have just used a small variation of the parameter alpha given in that transformation. So plugging the small variation delta phi into this formula here, and using the fact that this is a symmetry of the action, we find 0, because delta S has to be 0 for symmetry of the action, is equal to alpha, an integral over the box, times d mu of this expression here. Since the integration over this box is arbitrary because we have not specified what the size or the shape of this box should be, the only possibility for this integral to be 0 for any box of any size and shape is that the integrand itself of the integral has to be vanishing. So this brings us to the conclusion that this total derivative here has to vanish. We can denote the term in brackets as j mu. So this is just this term in brackets here, j mu of x. And the statement that the action should vanish will be a statement on this term j mu. We can calculate this relation here explicitly by plugging again the explicit action or the explicit Lagrangian into this formula, and we find that j mu for the complex scalar field is given as I times phi star, derivative on phi, minus the complex conjugate. So that would be minus I phi d mu phi star. And that's the same as twice the imaginary part of phi d mu phi star. That's just this object here. So with this notation, we find that the invariance of the action under the classical conservation law gives us a classical, under the classical symmetry gives us a classical conservation law for this object here. And we call the object J mu the current density. And then the result that we found in the previous slides, namely that this expression has to be equal to 0, just becomes the classical conservation law, d mu J mu is 0. We can write J mu in components. So there's a time-like component rho, which you can think of as being the charge density, and a vector component J. And then the conservation law is just d mu J mu equal to the time derivative of rho plus the total divergence of J vector. If we integrate this result over an infinite spatial volume d3x, we find that we can exchange the time derivative and the integral over space such that we get d0, d3x of rho from this first term here. And the second term here will vanish because, again, it's an integral over all of space of a total divergence of a quantity, and that will vanish by Gauss's law as long as j falls sufficiently fast at infinity. So putting these things together, we find that the time derivative of the integral d3x over rho has to be 0. If we sort of give this thing here a name, we can call this the total charge. And then this just says that the time derivative of the charge is 0. That means that the charge has to be constant in time. and that's just saying that the charge has to be conserved. So we found that the symmetry that we have found for our action gives rise to a conserved charge Q d3x rho, and this conserved charge Q fulfills a classical conservation law. The current density that's associated with this charge, J mu, is called the Neuter current. And the Neuter theorem generalizes this finding that we have derived in this lecture, saying that every continuous symmetry of the action corresponds to a conserved quantity. As such, it is an extremely important result in physics. Just to remind you, one of the applications of this Neuter theorem is that we can look at any symmetry that we have for S, for instance, Lorentz symmetry, or just symmetry under translations, which just shift space or we shift time. And any one of these symmetries has to give rise to a conserved quantity. In particular, the symmetry under translations, both in time and in space, must give rise to the conservation of a quantity that we call energy and another quantity that we call momentum. So the consequence of having a symmetry of our description that is invariant under changes of space or changes in time, so basically saying that the laws of physics should be invariant today and tomorrow, necessarily gives rise to exact conservation of energy, for instance. So this is a very deep consequence for our understanding of how nature works. And this concludes the present lecture.